All right, let's work number one. We are looking at several enolate type addition problems where we're adding carbon-carbon bonds to the alpha carbon of these various different reagents. And so I'll scroll through to kind of show the problem here in its entirety from exam 3. And one of the things I've done to prepare for this video key is I've drawn out the structures of each of these reagents that are listed. So that's part of the problem here, is getting to the structure that we're given. So for the first one with diethyl hexane dioate, we want to match up. Okay, the hexane portion is 6 carbons. The diethyl portion means the alkyl group on the ester carbon, and then the O8 ending again indicates the ester, and so we've got this compound. Okay, and so that's what we want to start with, are the different reagents. Diethyl malonate, on the other hand, okay, malonic acid is this 3-carbon dicarboxylic acid. When we add ethyl groups to it, it becomes a malonate from malonic acid, and essentially it's now the diester. So this is the malonic ester synthesis here that we see for the second one. Okay, diethyl benzene dicarboxylate. So we've got benzene, the parent chain here. We've got dicarboxylate. That would be the 1,2 substitution pattern that we see. And then when we add ethyl groups to those, we get a diester. Okay, so again, diethyl here. And then finally, acetone, 3-carbon ketone, our common name for that. And then cyclohexane carbaldehyde would be our aldehyde, not a benzene ring, but a cyclohexane here. That's benzaldehyde I drew. Fix that, the cyclohexane carbaldehyde, with the aldehyde being the parent chain there. Formaldehyde's the 1-carbon aldehyde. All right, so we've got all of our structures here drawn, and now we can begin the problem. All right, so with sodium ethoxide is being added, followed by HCl workup, and we see this diester. We add a base to a diester. We're thinking of an intramolecular Claisen, which is known as the Dieckmann condensation. And so the Dieckmann condensation is going to deprotonate one of these alpha carbons. There are 4 that we have to pick from that are all equivalent. We can just grab one of them. We can either show the alpha carbanon or we can show the enolate form. At this point, we have generated our nucleophile. So again, I could have shown the alpha carbanon. I'm going to show the enolate here, more stable contributor. Okay, and so now that can then add the Claisen alpha carbon connects 1, 2, 3, 4, 5-membered ring, where this alpha carbon connects back over to the other ester. We counted out our carbons so that we know how big to make the ring. At carbon 1, we've got a carbonyl now, and our original ester still connected. At carbon 1, 2, 3, 4, and 5, we've got our new tetrahedral intermediate. To finish out the Claisen, we know we're going to make a beta keto ester. So the tetrahedral intermediate collapses. It forms a new enolate because we just generated a base. That's why we have an HCl workup step to lock us in with our ester. So as we drew it here, we've got our beta keto ester product here. 3 points for the first structure. Looking at number 2, malonic ester synthesis, we're going to create the malonate. Again, alpha proton is deprotonated. Show the alpha carbanion this time instead of the enolate. And then it's an efficient acid-base reaction because the pKa of these dicarbonyl functional groups are lower, and so we have an efficient transfer. We get a very high yield of our basic form, and we're set up for an alkyl addition. We're adding isobutyl bromide, so 1, 2, 3, 4 carbons and a bromine. Substitution reaction here, and we get our product. See, I missed a carbon. Let me add that carbon back in. We've got to have the alpha carbon, but then we've also got to have all 4 of these. So again, being careful, 4 carbons from the alkyl halide, and then all my carbons here from the malonic ester as well. At this point, we do H3O plus and heat, strong acid, aqueous acid, heating to first hydrolyze the esters, and then the heating will decarboxylate one of the carboxylic acids that results from reforming the malonic acid. Okay, so the final product here, after the decarboxylation, we're going to have the carboxylic acid, the alpha carbon, and then the isobutyl bromide. So overall, 1, 2, 3, 4, 5 carbons with the methyl group added as well. All right, so we're going to add a slow addition of ethyl acetate. What we've got here is a mixture of this benzene dicarboxylate ester where we already have base in solution. And so if this attacks a carbonyl, the tetrahedral intermediate just kicks it right back off and we're back to our starting material. There are no alpha hydrogens in this diester, and so we don't need to use LDA. We don't need to use a dangerous base, expensive base, when we can just use a simple ethoxide base and then slowly add ethyl acetate. So let's see what happens here when we slowly add acetic acid. Okay, is the root term, and then acetate is the ester form, and so ethyl acetate, there it is. So it does have 1 alpha carbon, there's 1 set of alpha protons. So what this does is it generates, in an acid-base reaction with ethoxide, it generates the enolate form, or alpha carbanion if you prefer, of ethyl acetate in very low concentration. What else is in low concentration? The original dropwise addition or slow addition of ethyl acetate. So what does this see? This enolate sees a very high concentration of our diester. Okay, so the first thing that happens here is that we create a tetrahedral intermediate with one of these 2 esters. They're equivalent, so it doesn't matter which one you've added. There's my alpha carbon. We just regenerated the carbonyl. Now we've got our new ester here. Okay, so again, counting carbons, making sure we've got everything in place from our previous structure. Okay, so we want to make sure of that. Now, at this point, we've also got what was left over is this other portion of the tetrahedral intermediate that can get kicked off here. So the reaction is a Claisen reaction. Esters in base, okay, adding, creates a beta keto ester. So the first thing that happens, we form our beta keto ester. Just going to flip that bond, rotate it upside down so we get everything drawn out. I've got 1, 2, 3, 1, 2, 3 still. Beta keto ester, there it is. But I just generated again this base. Okay, so this acidic alpha carbon that we've just formed between the two carbonyls will regenerate either alpha carbanon, enolate, whichever you prefer. This time I'll draw the alpha carbanon. We're doing it all over again here. We're regenerating a nucleophile. And now what can it reach? Well, it's just going to reach out and grab the ester next door, attack the carbonyl, new tetrahedral intermediate. How large is this? 1, 2, 3, 4, 5-membered ring from alpha carbon to carbonyl. We're almost there. Draw my 5-membered ring. Where'd everything go? Here, there, keeping track of all my carbons, and I get to this point. So what can it do? At this point, it can reform this carbonyl. We acidify, and it's done. Our original benzene here. We now have this double carbonyl connected in the middle to a new alpha carbon that's been acidified, so it remains in the final form here. Okay, so we had 2 consecutive Claisens. We ended up with 2 beta keto esters, essentially. So 2 beta carbons with carbonyls after a sequential Claisen. All right, so let's take acetone. This time we are going to add LDA because eventually we're going to have 2 sets of alpha carbons. Okay, so I'm going to clear some room here for our next setup. So we use LDA at cold temperatures because it's safer. There's no real kinetic or thermodynamic side, so the temperature really doesn't matter, but if possible, go safer, go colder with LDA. That's why we put it in there. So we make the enolate at 100% yield, or close enough, because of how basic LDA is. That way, when we add our next reagent here, which is ethyl acetate, it has alpha protons as well. And so it would create a problem if it were all in solution at the same time. We'd have acetone adding to itself. We'd have the enolate of the ester adding to itself. So we want to minimize that by doing a crossed addition with LDA. Now we ensure that the enolate adds to the proper carbonyl. Alpha carbon has created a tetrahedral intermediate on the ester side. It looks like this. Tetrahedral intermediate collapses, kicks off the leaving group, and we are left with the diketone. The left half is from acetone, the right half is from ethyl acetate. Can't tell them apart. Either way you draw, it's fine. But essentially, the enolate alpha carbon half came from acetone, the beta carbon half came from ethyl acetate in the crossed addition. All right, so we're going to add dimethylamine and trace acid to our aldehyde here. That is the recipe for an enamine. Secondary amine adds to a carbonyl. So we make our enamine. Excuse me, on the other side, added a carbon. The enamine will add to this side. Okay, because again, that's a hydrogen, can't add that side. Add back to the carbon side there, the enamine. So there's the new alpha carbon. From there, we are asked to add 2-propenal. There's propenal. It's a beta, alpha beta unsaturated aldehyde. And it turns out that enamines are good Michael type nucleophiles. They prefer beta addition because they're soft nucleophiles. They're weak bases compared to enolates and so they prefer a beta addition very strongly, and we add to that beta position. So let's keep track of all our carbons here. We formed an iminium ion there, and then we've attacked the beta carbon. So here's the beta carbon we just attacked. There's the alpha carbon that we just attacked, and it created an enolate that when we hydrolyze with HClH2O, we're going to hydrolyze the enamine or the iminium back to the aldehyde that was there originally, and then we have beta, alpha, enolate will tautomerize back to the aldehyde that was on propanol originally. So counting up all our carbons, we've got everything accounted for, and that's exactly what we have for our answer. The original alpha, our original aldehyde, and then beta carbon, alpha carbon, and then the aldehyde from propanol after hydrolysis. Finally, formaldehyde can be in the same solution as hydroxide. Again, there's no alpha carbons with hydrogens on them for formaldehyde. It's just a one carbon-carbonyl compound. We add a slow addition of cyclohexanone to provide alpha carbons for our enolate formation. So hydroxide and cyclohexanone react. They form an enolate in very low concentration compared to formaldehyde. So what does this enolate see? It doesn't see more cyclohexanone because it's reacting with hydroxide, if slowly or if to a light degree. But because we've added cyclohexanone slowly, the concentration of formaldehyde is vastly greater, and so we're attracted to that formaldehyde in greater percentage odds. Once we do that addition, our alpha carbon has now connected. We've kicked up to an O- here, and we are free to acidify with HCl, completing what is an aldol reaction, a crossed aldol reaction, where the alpha carbon of the cyclohexanone has added to the carbonyl of formaldehyde. So beta hydroxy ketone for our crossed aldol reaction product.